Hello once again, class, and welcome to another mock lecture. Today is a bit of a longer video, at least slide-wise, and it took me forever to write, so I'm really hoping I don't find any typos, because I really don't want to re-record this whole thing. You might notice that I'm using a different background color. You're going to have to let me know if you guys like this over the kind of blinding white that I typically use, but I'm thinking about using this going forward. Leave a comment below, let me know what you think. Anyway, today we're learning about defining the other trig functions using the unit circle. At this point, we already know the definitions of the unit circle for sine and cosine, and we're going to use those ideas to help redefine the secant, cosecant, tangent, and cotangent functions. Well, let's get to it. So first off, here's kind of what we already know, right? We know that on the unit circle, which has a radius of 1, centered at the origin, that the adjacent side of an angle theta, that's cosine, and the opposite side of an angle theta, that is sine. And again, here's kind of our goal. I just said it like 5 seconds ago, but here it is again. We're going to redefine the other 4 trig functions using the stuff that we already know about sine and cosine, starting with the tangent function. Now, from right triangle trigonometry, we know that tangent is opposite over adjacent, so that's b over a. Well, b is the sine function, and a is the cosine function. So tangent can be redefined on the unit circle as sine over cosine. And actually, there's 2 physical representations we can give tangent on the unit circle as well. One of them is the fact that because the hypotenuse has a length of 1, right? It's a radius of the unit circle, then we can get from 0, 0 to AB by doing rise over run, which is actually B over A. So tangent is actually one way that you can interpret it. It's the slope of the terminal side of angle theta, which is pretty cool. There's actually another physical length we can give tangent as well, but you're going to have to stick around to the end of the video to find that out. And that's my kind of cliffhanger for, 15 minutes. Anyway, let's graph the tangent function. So first of all, what I did here is I set this up. We're just going to graph this thing from negative pi over 2 to 3 pi over 4. And if you've watched some videos on YouTube before, you're probably thinking, Mock, that is a really weird interval. I know. I just couldn't fit more than that, so that's all I did. So we need to fill out sine and cosine here by looking at the unit circle. So I've provided it here. If you want to pause the video and fill out sine and cosine, be my guest. If you're an absolute baller and you don't need the unit circle to fill this out, well then here you go, right? Here's what it looks like. So we need to figure out tangent, which is sine divided by cosine. So the way that I've organized this is we're just dividing all of this stuff by the things underneath it. So I set it up kind of like in a numerator denominator sort of situation already. You'll notice though that right here and right here there's kind of already a problem because 0 is going to be the denominator. So what happens is tangent is actually undefined at these pi over 2 values, negative pi over 2, positive pi, really anywhere that cosine is negative, right? Which is 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, right? So on and so forth. And then all the negative pi over 2 stuff as well. So we can't really graph anything right now based on those things. So let's move on to the pi over 3 stuff. To figure this out, right, and the tangent of negative pi over 3 and pi over 3 and 2 pi over 3 is negative square root of 3 or positive. How I figured that out was just doing some division, right? So negative square root 3 over 2, that's the sine of pi over 3. We're going to divide that by the cosine of pi over 3, which is 1/2. When you divide fractions, you always flip and multiply. So this is the same thing as negative root 3 over 2 times 2 over 1. The 2's cancel, so you just get negative root 3. Or positive root 3 for pi over 3. So I went ahead and I kind of did the best I could at approximating where those values are. For negative pi over 3, for pi over 3, and for 2 pi over 3. Okay, moving on to the pi over 4 stuff. This one is quite nice because you're dividing something by itself. One of them might be negative, so you're either getting -1 or +1. Okay, so those ones were pretty easy to graph. Whoops, that's the wrong one, not this one. -1 for negative pi over 4, 1 for pi over 4, and -1 again for 3 pi over 4. All right, negative pi over 6, similar stuff with dividing and flipping and multiplying and rationalizing in this case to give me negative root 3 over 3 at negative pi over 6. But at pi over 6, that's square root 3 over 3, so positive values there. Right, and that's what those are. And then finally at 0, we get 0 because 0 divided by anything is going to be 0. Unless you're dividing by 0, in which case it's an indeterminate form, which we'll talk later on in calculus. Okay, so this is the graph, right? This is actually not the whole graph, right? Because there's obviously more stuff to do on either side of it. But you just copy paste this thing a bunch of times because the period for tangent is actually 1. These vertical asymptotes are because of these undefined sections, right, that we're getting. Anytime you get 0 in the denominator for some kind of division function like tangent, you typically get these things called vertical asymptotes. Because as the denominator gets closer and closer to 0, and this thing, maybe it stays the same, maybe it's getting bigger, what's happening is you're dividing any number by something that's really, really small, and that blows up, right? Either in a negative direction or a positive direction. So we're getting these vertical asymptotes. To kind of really quickly recap asymptotes, you might have talked about them in another pre-calculus class, but they're essentially they're not actually part of the graph. I like to draw them in because they act as kind of like guidelines or little barriers for the function, and then I think it's visually nice to see where they're at. So I always draw them in. But basically, whenever a function exemplifies this approaching negative infinity or approaching positive infinity behavior, we can surmise that there are vertical asymptotes, right, somewhere in the graph. There's also horizontal asymptotes, but none of the trig functions that we've talked about so far exemplify horizontal asymptotes. You're going to have to wait till we talk about inverse trig functions for those to show up. Anyway, like I said, you just copy paste this a bunch of times, and that is the graph of tangent. Here's a Desmos drawing. That's way better than anything that I could draw. Again, the period is 1, and I think let's address this, because you might be wondering, why is it 1? Why is the period 1 when sine and cosine have a period of 2 pi? Why is the period 1 pi, to be specific? I keep saying 1, but I mean 1 pi. Well, you have to look at the unit circle, specifically where sine and cosine are positive and negative. Notice that in quadrant 1, you're dividing a positive by positive, and quadrant 1 starts here and ends here. You're dividing a positive by positive, so tangent is all positive stuff, right? It's all above the x-axis. Then you move into quadrant 2, and you're dividing a negative, or you're dividing a positive by a negative, and that's all negative stuff. So you get your vertical asymptote at pi over 2, that's what this thing is. And then in quadrant 2, which goes from here to here, tangent's all negative, right? It's all negative. And to be really clear, that is 1 period. I mean, I like to do it so that you show the period where it's all a nice continuous function instead of an asymptotic discontinuity in the middle of the graph. But that's quadrant 1 and that's quadrant 2. And that basically just gets repeated, because when you get into quadrant 3, you're dividing a negative by a negative, but a negative divided by a negative is positive again. So we get this part of the graph over on quadrant 3. So and then similar with quadrant 4, it's the same as quadrant 2, right? And that's why we're getting this thing. So the tangent function is really interesting because its period is half the width, right, of sine and cosine, and it's just because the nature of division gives us 2 repetitions of the function within a normal sine and cosine period. So the domain of the tangent function is you can plug anything you want into it except for these pi over 2 increments. So the way that I said it was set builder notation here. Theta, it's all theta values, right? All real numbers theta, such that theta is not equal to pi over 2 plus pi n, where n is an integer. So you're taking pi over 2 and you're adding whole numbered pi's to it, and that is going to make it so that you always get like 5 pi over 2 or 7 pi over 2 or negative 11 pi over 2. Some number of pi over 2 is always going to be a vertical asymptote. It's always going to give you something undefined for the tangent function, because that's where cosine's negative. The range, though, right, that's the interesting thing about tangent, because sine and cosine can only oscillate between -1 and 1. Their lengths have to be somewhere inside the unit circle, right? So they're capped at 1 and -1 for cosine, or 1 and -1, right, for sine. But tangent can be any number, right? You can get anything from negative infinity to positive infinity. So that, ladies and gentlemen, is the tangent function. Don't worry, we're not going to spend this much time developing cotangent, cosecant, and secant. But I think it's always good to go through tangent. Okay, next is cotangent. Cotangent is adjacent over opposite. from right triangle trigonometry? Well, that's the reciprocal of tangent, right? It's cosine over sine. These are reciprocals here. So another way we can define cotangent is 1 over tangent. And honestly, that's the easier way to go when you're graphing this thing, because you're just reciprocating. Is that a word? You're just taking the reciprocal of the tangent outputs. And so I decided to use really easy values for this. And I guess maybe the thing to point out is wherever tangent has a vertical asymptote, right? It's like technically something like this. At, let's see, at negative pi over 2, we're down here. So yeah, sine's negative. So it's negative 1 over 0. Well, the reciprocal of negative 1 over 0 is 0 over negative 1. Well, you can do that. That's 0. But when you have 0 for tangent, then you're putting 0 in the denominator. And so now the vertical asymptotes appear at all the whole numbered pi's. And I'll show you that here when we look at the graph. But I just chose really easy values to kind of show you we didn't need to go through all the pi over 3 and pi over 6 stuff. But this is the graph of cotangent. And again, notice that it's the whole numbered pi's and 0, where you're getting your vertical asymptotes. It's kind of like a reflection of the tangent function. Again, we see that the period is 1, but that is the graph of cotangent. Okay, domain is now all the real number theta stuff where it's not some whole number pi. And we also find that the range is similarly negative infinity to infinity, same as the tangent function. Okay, cosecant and secant from right triangle trigonometry are 1 over b, right? Hypotenuse over opposite for cosecant. Well, that's 1 over sine on the unit circle. Secant is 1 over the adjacent, hypotenuse over adjacent. In the unit circle, that's 1 over cosine. So again, when we're setting this thing up for graphing, I just made it so that we're just really easily going to fill out cosine and sine here. So we get all this stuff. And then secant is the reciprocal of cosine. So you can pause the video and take a look at this if you'd like. I'm just doing reciprocal and rationalizing when I can. So I'm flipping all of these, right, fractions, and then rationalizing when that gives me a square root in the denominator. And then here is cosecant, the reciprocal of sine. By the way, you know, when I was learning this stuff, I always wanted cosine and cosecant to be reciprocals because they both start with C, but that is not the case, right? Secant is the reciprocal of cosine. Cosecant is the reciprocal of sine. So the way that I remember, you know, which one is the reciprocal of the other, it's always what I don't want it to be. That's how I remember it. So secant, I want it to be sine's reciprocal. It's not, so I know it's cosine's reciprocal. Cosecant is sine's reciprocal. Anyway, graphing these things gives you this. And I think, you know, again, for cosecant, where sine is the denominator, it's all the whole numbered pi's where we get these vertical asymptotes because that makes sine 0. For secant, it's when cosine's 0 in the denominator that we get the vertical asymptotes, and that's at all the pi over 2 stuff. So anytime 0's in the denominator, we're going to get a vertical asymptote for this trig stuff. And so we're just looking at it. Okay, well, sine is 0 at all the whole numbered pi's. Cosine is 0 at all the pi over 2 incrementation stuff, but not the whole numbered pi's. So secant has vertical asymptotes at all those pi over 2 values, and cosecant has all those vertical asymptotes at all the whole numbered pi's. It's the range that I think is interesting for cosecant and secant. Just like with tangent and cotangent, we get negative infinity to negative 1, so it's almost like we're on the outside of the unit circle, right, for this stuff. We never get anything that's in between, right? No length inside of the unit circle for cosecant and secant. And I would be remiss to not mention that if you graph sine and cosine together with these functions, you get kind of a cool looking, you know, graph. They're always meeting at their hills and valleys, which I always thought was cool and visually pleasing, at least when you're looking at these things, and helps me remember, you know, what does the graph of cosecant look like? Well, if I'm looking at sine, I know that at all the hills and valleys, there's going to be like a kind of a, it's not really a parabola, but a parabola-ish looking thing kind of moving away from where the hills and valleys, where the local extrema are for sine. So those are all the trig functions. If you want to screen cap this and put it on your notes, that'd be something I think worthwhile. All right. Now, our book also goes through these things called, they just classify these definitions. So tangent being sine over cosine and cotangent being cosine over sine, those are called quotient identities. And then there's the reciprocal identities, which is just saying that each function is a reciprocal of another trig function. Right now, that's not super important, but once we get into identity proofs and identity verification stuff, the identities become a really big deal, and they're super useful in calculus and in trigonometric proofs. So we're going to return to these. I just want to point out that they do exist. That's kind of how we're defining them. All right, so we just spent a good amount of time going through all the setup that we needed. Surely we can do a ton of stuff with everything that we just learned. So let's go through some examples. Actually, we can really just evaluate trig functions. That's kind of it. There are some applications we're going to get to, but mostly we're just going to be still using the unit circle to evaluate trig functions, except now we can evaluate all of them. Okay, so the first example I'm going to go through is the secant of 17 pi over 6. I want to find an exact value. So I think that's the reciprocal of cosine. So it's the same as 1 over cosine 17 pi over 6. And we already know how to evaluate 17 pi over 6 for cosine, right? That's not new. Really, the new part was being able to write this. We did all that work just so that we could do something like this. Now, again, I'm not undermining the importance of being able to do this because this is very important. But as far as what we can do with it, right now, we're a little bit kind of still limited. Anyway, let's go through this. So, okay, cosine 17 pi over 6. It's got a reference angle of pi over 6. So I know it looks like this. Pi over 6 for cosine is the square root 3 over 2 thing. Now I just need to figure out what quadrant it is it in. So 17 pi over 6, or 17 sixths, is the same as 2 and 5 sixths. So then I'm just going to cross out the 2 because that's just coincident. That's just coterminal with 0. So then I'm just going to go pi over 6. Pi over 6 is in quadrant 2, so cosine's negative. So this has to be negative square root 3 over 2. The reciprocal of negative square root 3 over 2 is negative 2 over square root 3. And if you rationalize that thing, you get negative 2 square root 3 over 3. Okay, next one. Cotangent, negative 10 pi. All right, well, first of all, it's a whole numbered pi. At whole numbered pi, sine is 0. Okay, well, in the denominator for cotangent, sine is the denominator, so this has to be undefined. Right? Sine of a whole number pi is 0, so this is just undefined. Easy. Next one. Tangent of 13 pi over 3. Okay, well, this is sine of 13 pi over 3 divided by the cosine of 13 pi over 3. Pi over 3 is the reference angle, right? So then we just need to look at where are we on the unit circle. So for 5 pi, right, that's coterminal with pi. So we're here, and then we're going to still rotate another pi over 3. So we're in quadrant 3, and the reference angle, or I guess the xy coordinates for pi over 3 is always 1/2 for cosine and square root 3 over 2 for sine. Since we're in quadrant 3, both of them are negative. So we're dividing the negative square root 3 over 2 by negative 1/2. I would write it like this, so you can flip and multiply that second one. The 2's cancel and the negatives cancel, so we just get the square root of 3. Here's another thing we can do, and this one's a little bit more involved. It's something that we have done before, but now we can use all the trig functions. So it says determine the values of the trigonometric functions of theta by using the given information. So we know that the secant of theta is 25 sevenths, and we also know cosecant theta is 0. And so again, to kind of reiterate the question, what's the sine of theta? What's the cosine of theta? What's the tangent of theta? What's the cotangent of theta? What's the cosecant of theta, right? We don't even know that. We just know it's less than 0. Okay, so there's a little bit of stuff to unpack here. First of all, let's figure out what quadrant we're in. Well, we know that secant is positive and that cosecant is negative, right? So those are the two things that we know kind of just by looking at the problem. Well, if cosecant's negative, that means the reciprocal of cosecant is also negative, so sine's negative. And if secant is positive, that means the reciprocal, cosine, is also going to be positive. So where on the unit circle is sine negative and cosine positive? There's only one place, and that is quadrant 4. So I'm going to go ahead and draw myself a triangle where the hypotenuse length is 25, because secant is hypotenuse over adjacent. So I've got 25 here as the hypotenuse. 7, right, is the adjacent side. Whatever this is going to be negative because we're in quadrant 4, and that's a negative value here. So we can solve for it by using a variant of the Pythagorean theorem. In this case, b squared is equal to c squared minus a squared. And so here's my math. And when I took the square root of 576, you get plus or minus 24. Since we're in quadrant 4, we know it to be negative 24, so this is negative 24. And now we can just write all the trig functions, right? Really based on right triangle trig, kind of at this point. Cosine is adjacent. Well, cosine is actually just the reciprocal of this thing, so you could just flip that. Cosecant is, dang it. I am not going to re-record this. This is negative 25 over 24. Yeah, that's cosecant. Sine, though, is opposite over hypotenuse. That's negative 24 over 25. But yeah, there is a typo there. Tangent is opposite over adjacent, so negative 24 over 7. And cotangent is just the reciprocal of that thing. Okay? And I did want to fit in one kind of application example. Okay? So there's this thing called atmospheric refraction. The Earth's atmosphere refracts some light at specific angles when it enters the Earth's atmosphere. So things we see are actually not exactly where they are in space. So in this example, I'm drawing kind of the angle alpha that we're kind of looking up at the star at. But then the atmosphere refracts that by some angle measurement theta. So there's what we call an apparent position, that's what we see, and an actual position. So the solid line here is kind of where the star actually is, and as that light enters the atmosphere, it gets refracted a little bit, and that's what atmospheric refraction is. It's not unlike when you put like a straw or something in a cup of water, and then it looks like the straw is bent. It's not actually straight. That's the same sort of thing that's happening. That's what the atmosphere does to light that enters it. All right, there is a formula, which I'm just going to give us, and it's the amount that starlight is refracted in seconds. So that's DMS stuff, is theta. So theta is in seconds, and it is the formula 57.3 times the tangent of alpha. But this formula only holds true when alpha is inside of the interval 0 to 45 degrees. So for an example, let's suppose that alpha is 25.7 degrees. What is the angle of refraction? Well, I mean, it's not really that complicated of an example since we're just kind of plugging stuff into the formula. We know alpha is 25.7. You just run this through your calculator, make sure that it's in degrees, and you get 27.57 seconds. So that means that the light is bent about 27.57 seconds, right? So it's that much lower in the sky than what we're actually seeing it at. So hopefully this video was helpful. I know it was kind of a lot to kind of set up for not really that complicated of example stuff, but those definitions of the trig functions are super important. All right, so if you have any questions or comments, please leave them in the comment section. Thanks a ton for watching, and I'll see you in the next one. Bonus knowledge! Okay, so I had mentioned before, right, that you can see the lengths of all these trig functions on the unit circle. If I did not mention that, I'm mentioning it now. You can see all the lengths of the trig functions on the unit circle, just like you can see sine and cosine. Here's how they look. What I'm going to do is I am going to draw a tangent line, and that might give you an indication for what we're about to look at here. A tangent line to the unit circle that meets the extended part of the terminal side of the angle theta. Okay, so the tangent line of the unit circle is perpendicular to the x-axis. I just drew it straight up here. And then I'm extending the terminal side of the angle, and I'm going to look at where they meet. I want to find this length. Well, we have similar triangles here. Okay, we've got kind of this big triangle, and then we've got the normal unit circle triangle. So I can set up the ratio question mark over 1, right, in the big triangle, is the same as sine over cosine, right? Height over this base. Because similar triangles, well, sine over cosine is tangent. So here's tangent on the unit circle. It is a physical length on the unit circle. It's outside the unit circle, but there you go. That's the tangent function. And as this angle increases, right, tangent becomes bigger and bigger, right? Say you have like 89 degrees, right? Tangent's going to be massive, right? That's why its range goes to infinity. Okay, what about this length? Okay, this length can also be set up using similar triangles. Question mark over 1. So we have this triangle again, right? This side length, the hypotenuse over 1, that's the same as 1, because we're inside the unit circle, over cosine, right? Hypotenuse over base, basically. Well, 1 over cosine, that's the secant function, So here's secant on the unit circle. Okay, cotangent and cotangent and cosecant rather, can be set up in a similar way, except this time I'm drawing a tangent line to the unit circle that's parallel with the x-axis up at 0, 1. And again, I'm still extending the terminal side of angle theta here. But what's weird is that we get a right triangle that doesn't involve theta in this case, right? We get this right triangle. But that's fine. We're going to call that theta, that measurement alpha, okay? And if we set up a tangent of alpha, right, tangent is opposite over adjacent, right? So in this case, it's question mark over 1. The thing to know, though, is that alpha and theta are complementary angles. So we could rewrite alpha in terms of theta by writing it as 90 degrees minus theta. Now, in one of my videos, we talked very briefly about cofunctions, and this is a cofunction for the cotangent of theta. So I'm just going to replace that with cotangent theta. So there you go. Right, here's cotangent. Cotangent is this length here. Similarly, we can do cofunction stuff to show that this length is cosecant, the extended side of the terminal side of angle theta. But it's not the same terminal side as angle theta that represents secant, because it's a different tangent line that we've drawn. So this one's actually, in my picture at least, longer than the secant line. In any case, here's all the trig functions on the unit circle. And I think that it's important to know that cotangent, cosecant make a right triangle, okay, with one of its side lengths as 1. Sine and cosine obviously make a right triangle, right, with one of its side lengths as 1, and this one's the hypotenuse. And so do tangent and secant, right? So secant, tangent kind of go in a pair, coming up in an identity soon. Cotangent and cosecant come in a pair, right? And it's all right triangle stuff. So you can imagine Pythagorean stuff is going to be involved, and then also sine and cosine. So cotangent and cosecant are kind of linked via some identity that we're going to get to, and same with tangent and secant, as well as cosine and sine. Anyway, hope that was interesting. Again, thanks a ton for watching, and I'll see you in the next one.